What is machine learning? Herbert Simon, an American economist and cognitive psychologist, defined learning as a process by which a system improves its performance from experiences. Tom Mischel, a Carnegie Mellon University professor in computer science and a long contributor in machine learning and expertise in artificial intelligence, defines machine learning as the study of algorithms that improve performance P at some task T with experience E. So P, T, and E, performance, task, and experience, these are going to be the components that define machine learning. You may be wondering what is the difference between programming, traditional programming that we know it, and machine learning. To put it in a simple way, in traditional programming, we give the data to the computer and tell it what to do and how to do things for us. And the computer simply listens to us and follows the order and performs the task that we want it to do in a very efficient way and gives us the results. Not very intelligent. Actually, the intelligence comes from us, not the computer. In machine learning, however, we give the data to the computer and tell it what we want. This is especially true in supervised learning. And the computer has to learn by itself how to do to get the output that we want from it. So the computer has to play an intelligence role here, not just follows simple tasks. Arthur Samuel defines machine learning as a field of study that gives computers the ability to learn without being explicitly programmed what to do. When and where to use machine learning? Machine learning is used when human expertise does not exist because, for example, exploration or navigation is unaffordable or dangerous, such as navigating another planet, or where human cannot explain their expertise. For example, in speech recognition, you can definitely recognize your mom's voice, but could you explain that skill to someone else and teach him how to recognize your mom's voice? Or when models or products, for example, need to be customized for the endpoints at the consumption, personalized medicine is an example of that, or when models have to be based on huge or lots of data, such as in genomics. But learning is not always useful or even necessary. For example, for a simple task such as calculating payrolls, we don't need machine learning. A classical example of a task that could use machine learning is handwriting recognition. In handwriting recognition, similar to voice recognition, we can't really explain how to recognize someone else's handwriting, even if we ourselves know and are capable of recognizing someone else's handwriting. Therefore, handwriting recognition is a perfect task for machine learning. Let's see more examples of problems that can best be solved by machine learning. Machine learning can be used in recognizing patterns. For example, recognizing facial identities or facial expressions, or handwriting or spoken words, which are already talked about them, handwriting and speech recognition, or in reading and analyzing medical images, For example, to identify whether someone has tumors or not, identifying tumors, recognizing tumors in the early stage. Machine learning can also be used in recognizing anomalies. Anomalies are strange data values that do not conform to the overall pattern or structure. An example of anomaly is outlier. For example, machine learning can be used to track unusual credit card transactions for potential fraud activity. Machine learning can be used for predictions. For example, future stock prices or currency exchange rates. Defining the learning task. So we learned that machine learning can be defined as improving on task T with respect to performance metric P and based on experience E. Examples of these can be, for example, the task can be recognizing handwritten words. The performance for this can be the percentage of words that are correctly recognized or classified. The experience here can be the database of human labeled images of handwritten words. Another example, the task can be categorizing email messages as spams or legitimate emails. The performance here would be the percentage of email messages that are correctly classified as spams or legitimate emails. The experience here would be the database of emails, some with human given labels as spam or legitimate. Let's see some state-of-the-art applications of machine learning. An example would be autonomous cars. You might have heard about some companies that are working on making cars that can drive by themselves without any need for a human driver, such as Uber or Tesla or Google. The autonomous car technology has to control all the movement of cars, including speed, steering, and brakes, and also has to recognize traffic and pedestrians and avoid engaging in any accidents. Another example would be a speech technology in some smart assistant systems, such as Google Assistant, the Microsoft Corona, the Apple Siri, or Amazon Alexa. These systems have to understand spoken words and respond to them in an intelligent way. Types of learning. Supervised or inductive learning. Supervised learning is the most common type of machine learning. Supervised machine learning algorithms are designed to learn by examples in a process that is called training, given input data that are labeled, meaning the input data are matched with their corresponding outputs. We call these data labeled. During the training process, the algorithm must search and identify hidden patterns and relationships between the pairs of input data. This process kind of mimics learning for the algorithm, learning the patterns or the relationships. After the training process, the trained algorithm will be given an unseen set of input data that is not labeled, meaning we don't really know the corresponding outcomes or outputs for these data. The algorithm has to determine the appropriate label for this data based on the training that it has had. So the objective of supervised machine learning models and algorithms is to predict the correct label for newly presented input data. In this course, we're only going to cover this type of machine learning. Next, we have the unsupervised learning. Unsupervised machine learning algorithms have to infer patterns and relationships from a dataset without any reference to known or labeled data. Unlike supervised machine learning algorithms, unsupervised machine learning algorithms do not have any reference or guidance because they do not have any prior knowledge or labeled data. Next, we have the informed learning. Reinforcement learning is a type of machine learning algorithms that work in a sequence of decisions in which the algorithm has to learn how to achieve a goal in a complex environment in a game-like situations, and it has to employ trials and errors to come up with a solution to the problem. In this process, the machine gets either rewards or penalties for its actions and performances. The goal for the algorithm is to maximize its total rewards. You might have already heard about deep learning and may be wondering what's the difference between the two, the machine learning and deep learning. Deep learning is considered an evolution of machine learning. It uses a programmable algorithms and methods such as neural networks that we're going to learn about later on to make accurate decisions without any help from us humans. For example, in deep learning, the feature extraction that is used in a classification algorithm that humans otherwise would have to specify and extract them would be done by the algorithm itself. For example, suppose that we want to design a classification algorithm such that we give them the car, we give the algorithm the car, and the car would specify different, classify the cars. So in this process, it is up to us, the humans, to extract a feature that can be used to distinguish cars from each other. For example, the shape of the car, the model of the car, the number of doors, the number of cylinders, or any other features that are important in distinguishing and classifying cars. This process, finding and extracting features, has to be done by the algorithm itself in deep learning. Machine learning in a nutshell. There are already thousands of machine learning algorithms, and probably hundreds of new algorithms are invented each year. But there are some commonality and common grounds between these different algorithms. Every machine algorithm has three components. First is representation. How to represent knowledge or type of algorithm. Choose a feature to represent. Next, we have the evaluation. What criterion to choose to evaluate the performance of your algorithm. And next is optimization. Choosing the best parameter or set of settings for your algorithm to yield the best performance of it. Various function representation. There are different types of representation in machine learning. We have numerical function representation. Examples of these are linear regression. We have artificial neural networks and support vector machines. We have symbolic functions. Example of these is decision trees. We also have instance-based functions. The example is nearest neighbors, such as k-nearest neighbor. We also have probabilistic graphical models. Example of these is the naive Bayes method. Generally, a machine learning algorithm in the learning process consider and inputs a set of samples of data and then tries to predict properties of unknown data. If each sample is more than just a single number, and for instance, a multi-dimensional entry as we have in multivariate data, it is said to have several attributes or features, as you see in this table. For example, the student ID, first name, last name, major, year, etc. These are features or attributes. Learning problems. Learning problems fall into a few categories. The first of them is supervised learning. In supervised learning, data comes with additional attributes that we want to predict. The problem can be either a classification problem in which samples belong to two or more classes, and we wanted to learn from already labeled data that we know what classes they belong to how to predict the class of unlabeled data in which we don't know the class of the data. An example of a classification problem would be handwritten digit recognition, in which the aim is to assign each input vector to one of the finite number of discrete categories or classes. That's why it's called classification. The next is regression models. When the output consists of continuous variables, such as predicting the length of a salmon as a function of its weight and age, it's called a regression. You're already familiar with regression from statistics. As we have learned so far, one type of supervising algorithms is classification algorithms. There are two types of classification algorithms: binary classification and multi-class classification. In binary classification, there are only two classes or two labels. We use a labeled sample data to train our algorithm. The algorithm is usually called a classifier to learn the hidden relationship in our data. And then after the training process, the classifier will be given an unseen new set of data that is not labeled. And the goal of the classifier is to classify and label the data correctly. A familiar example for this type of classification is a spam detection in your beloved email service, such as Gmail, for example. In this example, the classifier has to learn how to distinguish a spam from legitimate email so that it could put the spams in the spam folder and put the legitimate emails in your inbox. You might have been bothered by mistakes that this algorithm have made so far. Another type of classification algorithms is multi-class classification algorithms. In multi-class classification algorithms, there are more than two classes or two labels for our data. For example, suppose we want to build an algorithm, a classifier, that is able to recognize the pictures of animals and label them correctly as to what type of animals they are. As you see here, we have pictures of cats, dogs, ducks, and rabbits. In the training process, each data point X is paired with a target value Y or a label Y, which is also called the classes. So we have paired data. The goal is to teach the classifier how to classify these animals and label them correctly. For example, label a picture of a cat as a cat. In a mathematical context, this means that the classifier has to learn a function f that could map a picture of, for example, a rabbit to a label of a rabbit. Suppose that the algorithm has not seen a picture of this particular picture of a rabbit. So based on the training that it has had before, it must be able to recognize this picture as a rabbit and classify it correctly as a rabbit, solely based on the training that it has had before. If you remember this in supervised learning, every data point X was paired with a target value Y, which was its label. In unsupervised learning, however, the data consists of a set of input vector X without any labeled data or corresponding target values. In unsupervised learning algorithm, the goal is to discover similar groups within the data. This method is known as clustering, or to determine the distribution of data within the input space, such as the density estimation, or to project the data from a higher dimension space down to 2 or 3 dimensions so that we could visualize the data. for the purpose of visualization.